In the Week 11 Foundations of Physics lab, we were given the task of building a velocity and acceleration sensor. The provided equipment included two cylindrical magnets, a plastic tube, thin copper wire, a ruler, a retort stand, and an oscilloscope, which measures voltage as a function of time. This equipment was possessed by a demonstrator who followed our group's instructions through a Zoom call. We immediately knew that there was a relationship between voltage and the velocity of a moving magnet from Lenz's law, which states that when a magnet moves through an electric field produced by a coil, the coil's current will experience a voltage change whose magnitude is equal to the magnetic field multiplied by the magnet width multiplied by the magnet's velocity. We figured the tube could be used to control the magnet's movement due to the unique size similarity between the tube's inner diameter and the diameter of the magnet. We decided the copper wire could be used as a coil around the tube, with the tube held upright by the retort stand. Doing this meant the magnet could be dropped down the tube and passed through the coil. Each end of the coiled wire was connected to the oscilloscope via alligator clips. However, if we were to apply Lenz's law, we still required to know the magnetic field of the magnet. We thought about using the Biot-Savart law, but that would have made the problem even harder, requiring us to know the charge quantity and distribution, which for a ferromagnet is fundamentally subatomic. We decided to go ahead with the experiment and observe what would happen to the voltage reading if the magnet was dropped through a single coil. This ended up producing a reading where the voltage decreased to a minimum, increased to a maximum, and then plateaued back to its original starting point. Although we did not know the magnitude of the magnetic field, we knew it existed, so we're still able to account for these trends. What happened was, when the first pole came close enough to the coil, the voltage decreased. Then, the second pole also came close enough, but produced an opposing effect, cancelling out the effect of the first one, and thereby bringing the voltage back to its set point. This inflection point was reached when the magnet's midpoint aligned exactly with the middle of the coil. As the magnet kept falling, the first pole got further away, while the second pole was still within range. This caused the voltage to keep increasing. This occurred until the second pole also became too far away, resulting in a reset back to the set point. Hence, this particular voltage reading displays the time interval at which the magnet travelled its own length. Ironically, we didn't even need to record the voltage, we just needed to identify this shape on the graph. To obtain the velocity at the particular moment, we just had to record the length of the magnet and divide by the time interval of this shape. The experiment was repeated, but instead with two coils of wire connected to the same circuit. This gave two readings of similar shape to the previous. However, the second one had taller peaks and was more squished in. This is because the magnet's speed increased the further down the tube it was, since it was accelerating due to gravity. By Lenz's law, velocity is proportional to change in voltage, which is why the peaks became taller when velocity was greater. The peaks were more squished in because a faster velocity meant the entire interaction occurred within a smaller period of time. Similar to before, the velocity at each of the two inflection points was approximated, and using the time difference between the points allowed average acceleration to be calculated. In particular, a value of 8.65 meters per second squared was obtained, which is quite close to the theoretical acceleration due to gravity on Earth's surface, approximately 9.8 meters per second squared. Our slightly lower reading was most likely attributed to friction between the magnet and the tube, which likely slowed the magnet down. Other negligible but noteworthy contributors include limits of accuracy with our measurement tools, including the oscilloscope itself, electromagnetic interactions with the magnet and the copper wire, and air resistance.